Hello, everyone. Welcome to the next talk in the Julia track. So today we have Guillaume Dalle. He's going to be talking about automatic differentiation in Python and Julia. Guillaume is a postdoc at EPFL, and I just learned he's going to be taking on a permanent position in Paris. And so look forward to a JuliaCon Paris in the future that I just heard he's working on. Without further ado, here's Guillaume.
Hi, everyone. Thanks, Mark, for the introduction. My name is Guillaume, and I'm going to tell you a little bit about what I've learned on automatic differentiation and how it compares between Python and Julia, which is the main language I work in. So first of all, you can find the slides here on my website, gdal.github.io/pydata2024-autodiff, or you can just scan the QR code. And while people maybe do that, I'm going to try this. So there's a poll asking you which autodiff libraries you've used before, and I guess we'll see if this thing works. Please don't make me feel alone. All right, strong showing for TensorFlow and PyTorch. Grand total of 2 users for PyTorch. Jack's coming in strong. Zygote in the back trying to catch up. All right, so as expected, the Python autodiff tools are obviously more popular in this community. And what I'm hoping to tell you a little bit about is how they work under the hood, what they can or cannot do, and how the situation differs in the Julia ecosystem. All right, so let's go back to the slides. And first, a little bit of motivation. What is differentiation? If you remember your math classes from undergrad, it's just about finding a linear approximation of a function around a point. And why do we even care about this? Because we use these derivatives in optimization and in machine learning. And not just derivatives of simple functions, but derivatives of actual computer programs. Now, what do we need to do to get these derivatives? Well, actually not so much. We just let automatic differentiation compute derivatives for us. But of course, that's a bit of a pipe dream. And in reality, it doesn't always work the way we plan. First of all, let's recap the basic flavors of differentiation because there's more than one. And as you can see, they each have their advantages and drawbacks. So I'll illustrate this with Julia code, but you'll see it's pretty readable. First of all, the only slide with math, the formal definition of a derivative. If you have a function that goes from a space with n dimension to a space with m dimensions, and you try to differentiate at a point x, what you get is a linear map, partial f, such that essentially taking a small perturbation of x results in f of x plus a linear term here plus plus an error that is essentially small compared to the perturbation. Now, this linear map, it has several names and it has several representations depending on the specific scenario. For instance, if you take a function from numbers to numbers, then you can just represent this linear map by a number as well. And we call this number the derivative. If you have several inputs but one output, you can usually represent this linear map by a gradient vector, nabla of f. And this is very useful, of course, in machine learning and deep learning, where most of the parameters in neural networks are learned by an algorithm called gradient descent. And finally, in the general case where you have several inputs and several outputs, you want to represent this derivative or this linear map with the matrix that's called the Jacobian, where each coefficient corresponds to the partial derivative of a specific output with respect to a specific input. At any point, if you have questions, feel free to use the chat or the Q&A bar, and I'll try to answer as best I can. So this is the only slide with math, and now we get to the fun part. How do we actually compute derivatives or differentials? The first one, of course, is manual differentiation, writing down formulas just like it's high school all over again. And as we'll see, it's really hard to generalize. For instance, if you have a very simple function, this is Julia code to compute a square root, then you can, of course, remember your high school and say that the derivative is 1 over 2 square root of x. That's great. But now let's say you have a slightly more complicated code which actually computes the same thing. This is something called Heron's method to compute the square root, and it's equivalent to the Newton iteration for finding a zero or a fixed point. So you do 3 iterations of this weird update, and you get something if you evaluate it at x equals 2, that is very close to the actual square root of 2. Now, of course, working out the derivative of this procedure by hand is a bit tricky because it's not just a mathematical function, it's a bit of computer code. It has a loop. You could have if-else statements, you could have while loops, you could have exceptions, you got things like that, make it very complicated. And so in the end, you're too lazy to compute the derivative. So this manual differentiation thing, it's what you start with, but it's labor intensive, it's error prone, and it's not what you want to do. So then, if you're lazy like me, you turn to Mathematica or Wolfram Alpha and you ask them to work out formulas for you. These systems are computer algebra systems, and they can usually compute derivatives and work out formulas that represent these derivatives at any point. That's really important, at any point. So again, when you do it on a simple function like f, you get a simple expression. But when you do it on a complicated function with loops, then you get this expression, which scrolls all the way to the right here. And as you can see, it's only going to get more complicated the more iterations you put in your loop. So the problem here is what's called expression swell. This symbolic differentiation thing, even when you try to simplify, it usually doesn't scale up to more complex functions. So instead, you can try to give up on having a generic formula to compute derivatives at any point, and you can say, okay, I'm going to stick to what I know and compute derivatives at one given point. And to do that, there's a great way, which is called finite differences. It essentially goes back to the definition of the derivative and says, okay, I can approximate my derivative by the difference between two function values at very close points divided by the distance between these points. And now, of course, the question is, how do you choose this epsilon, this little step that you take in those finite differences? Because if you choose it to be too large, then the approximation is no longer valid, and you get a derivative value that's not exactly the right one. If you take it just right, then you get a derivative value which can be rather precise. But if you take it too small, you would think it's even more precise, but actually you get into the realm of floating point errors and catastrophic cancellation between f of x and f of x plus epsilon. So this is a tricky problem, and the right choice for epsilon depends on the function that you're computing and on the specific precision that you're aiming for. So you have truncation or floating point errors here. And in addition, it can be rather slow, but we'll get back to that. So the method of choice nowadays is called automatic differentiation, but I don't really like this term because the previous methods that I've shown, with the exception of the manual one, they were also automatic in a sense. So I prefer to call this algorithmic differentiation because it's all about algorithms. It's about reinterpreting the program that computes the function to obtain the derivative instead. And here I show you one example of an implementation in Julia, which is very simple. It's called dual numbers. The idea is to carry around numbers that are actually a tuple containing both the value and the derivative of the corresponding value. So here, what you have to do next is you have to redefine the basic operations of your language to accommodate propagation of both values and derivatives. Here, for instance, when you multiply a dual number with a scalar, you multiply the value and you multiply the derivative. And you have more sophisticated formulas, for instance, for division, where you divide the values and then you do u prime v minus v prime u over v squared. That's the formula I learned by heart in high school. And so once you implement these basic operations, then you let these augmented numbers propagate through your program. And when you apply your functions to them, you get at the very end a number that contains both the primal value that you're interested in and the derivative that was sort of computed as a byproduct. So this is sort of the method of choice for computing derivatives, because unlike numeric differentiation, it's quote unquote numerically exact. Of course, that's not entirely true, but we're going to put this under the rug for the purpose of this talk. Now, what's the catch here? The catch is that this is much harder to implement than numeric differentiation, where you just evaluate your function twice. And it's really hard, especially when you want to do this efficiently. So now we're going to take a little peek at what happens under the hood. Under the hood, an algorithmic differentiation system is composed of two main ingredients. The first ingredient is the one you learn in high school. It's hard-coded derivatives for the basic functions that you can call in your language, the addition, multiplication, and then all of these fancy mathematical functions like x, log, sin, cos, etc. The second thing you need is composition, because from these basic functions, you build more sophisticated programs, and so you compute their derivatives in turn with the chain rule. If you have a composition of two functions, you know that the derivative, the linear map, is a composition of two linear maps. So essentially what algorithmic differentiation does is it takes a look at your function. If your function is something that can that has a primitive hard-coded derivative, it just returns that. And otherwise, it breaks the function apart into smaller individual components, subroutines, and goes and does that again recursively until it arrives at these hard-coded derivatives. Now, there are two main ways that you can do that. You can do these sort of breaking apart of the functions into their elementary components. One is called operator overloading, and it's the one I showed you before with these dual numbers. It's about defining new types that augment the runtime operations to store more information, in this case, storing the derivatives. This is what happens in PyTorch, where the tensors actually store their derivatives and what happens in the computations beforehand. On the other side, you have source transformation, which works in a way that is similar to a compiler. It takes the source code and pre-processes the source code before runtime at compile time to generate a new source code that computes derivatives alongside the function values. And this is, for instance, how JAX works. Now, you may have heard that algorithmic differentiation has two modes, forward mode and reverse mode. They correspond to very different implementations, and I don't have time to get into that. But I just want to stress one thing. If you have a function with many inputs and many outputs, forward mode automatic differentiation allows you to get all partial derivatives with respect to a given input. You propagate an input perturbation onto every single output at a cost that is roughly the cost of one function evaluation. So for one function evaluation, which is sort of the basic unit cost that you have in your program, right? Because you need to sort of go through every single operation inside f. So for a cost that is roughly the same, you get all partial derivatives with respect to one input. On the other hand, you have reverse mode automatic differentiation. And here, for the same cost, you get all partial derivatives for a given output. So it's not the same direction, it's the other direction where you backpropagate an output sensitivity onto the input variables. For a given output, you backpropagate onto every single input. And here, note the choice of word backpropagation is the word that machine learners invented to refer to reverse mode automatic differentiation because they couldn't be bothered to open a book and figure it out. But it's really important. It's the thing that makes deep learning possible. Why is deep learning possible? Because of reverse mode automatic differentiation specifically, because we can compute gradients really fast. Indeed, for gradients, the number of outputs is one. So for the cost that is roughly the same as one evaluation of the function, you get all partial derivatives which form your gradient vector. Now we get to the fun part where we talk about programming languages. And it turns out you have a variety of options to perform automatic or algorithmic differentiation. In Python, you are probably familiar with these three main AD frameworks, TensorFlow and JAX, which are developed by Google, and PyTorch, which is developed by Facebook. In Julia, you may be surprised to learn that we have a dozen or so AD backends. We have some that are forward mode, like forward diff. We have some that are reverse mode, like reverse diff. We have symbolic ones. We have numeric ones. We have the brand new enzyme, who's like the cool kid in town. And you may wonder why I call the ones in Python frameworks and the ones in Julia backends. The reason for that is because in Python, you do everything within the framework, whereas in Julia, the backend takes sort of a more hidden role and does not necessarily interfere with your code itself. To be precise, what happens in Python is that the first thing you do for your project is you pick a framework. You pick PyTorch, or you pick JAX, or you pick TensorFlow. And then, if you want to, for instance, solve optimization problems, or perform deep learning training, or solve differential equations, then you pick the implementation of, let's say, differential equations that is implemented in your framework of choice. So there's a for a given scientific topic foo, there's going to be a torch foo, and there's going to be a FOOCS, which is implemented in JAX. And the same for the other scientific topic bar. What happens in Julia is sort of the other way around. First, you pick what you want to do. You want to do differential equations, or you want to do optimization. And then there's a single package, foo.jl. But then it might be compatible, or it might want to use several solutions for automatic differentiation. So it's the other order of decision making. First, you choose what you want to do, and then you choose how you're going to compute gradients inside of that scientific application. Now, if you're a package developer, this also influences how you write your code. But in both cases, whether you select the AD framework first and then write, or whether you first write your code and then make it compatible with autodiff, in both cases, you have constraints that apply to you because not every single bit of code, whether it's in Python or in Julia, will be compatible with automatic differentiation. So even though you make decisions in the other direction, you also have to keep in mind that you're writing code that will eventually be used to compute gradients. Now, why is there such a difference between the two languages? The key thing that you have to keep in mind is that it's linked to mathematical operations and tensor types. If you're scared of the word tensor, just think of it as a vector or a matrix or a higher dimensional array, right? It's numpy.array or torch.tensor. The math and tensors in Python are framework specific. If you write code in PyTorch, you're going to use torch.tensor. If you write code in JAX, you're going to use jax.numpy. In Julia, these two things are part of the core language. There's the core array type, at least for CPU. I'm not talking about GPU, but for CPUs, the array type is part of the core language itself. And so that means that you don't actually need to commit to a specific framework to write basic code. But then you have to pick an AD library to differentiate through that code. In terms of AD developments, the two languages differ as well. In Python, it's very centralized. It's backed by very large companies with massive workforce. In Julia, it's very decentralized. It's basically a bunch of grad students doing this mainly in their spare time or sometimes for their research. But it's really small libraries, often with a bus factor of 2 or even 1. And that means the reliability, of course, is not the same as something that's industry proof like JAX or PyTorch. In Python, the limits of automatic differentiation are very well defined because as long as you stay within the field of experimentation that PyTorch or JAX allows you, well, you can't really go wrong, right? It's sort of a very well-defined area in which you're allowed to play around, and everything you do will always be differentiable. On the other hand, in Julia, each AD backend has a slightly different set of operations that it supports. Some AD backends do not support mutations, a la JAX. Other AD backends need specific types to work with. So it's a bit more complicated to find your way around this ecosystem because depending on the AD system that you choose, your code may or may not be differentiable. On the other hand, what you get from that, from the math and tensors being part of the core language, is that you don't have to split your effort for the scientific libraries that you want to write. You only have to write a single library for differential equations. It's called differentialequations.jl. You only need to write a single library for, I don't know, probabilistic programming or deep learning. And you don't need to split your effort by re-implementing this across every single autodiff system. Now, it doesn't really have to be this way. And the reason it is this way is because AD, automatic differentiation, is a post hoc addition to the language. But it could be a language feature. And I would argue that in 2024, if you write a new programming language, you need to make sure that it is differentiable. And in the end, that's what PyTorch, JAX, and friends are. They're new programming languages built on top of Python in which everything you do is differentiable. Whereas in Julia, the objective is to differentiate through the language itself, which is both more ambitious and more likely to fail. But it's worth it nonetheless. In this sort of fragmented ecosystem, what's really important is having experimentation options in the form of interfaces. I don't know if you noticed, but there's a very popular deep learning library called Keras, and it used to be TensorFlow only, but since its latest release this year, it supports TensorFlow, PyTorch, and JAX. So you don't have to rewrite your code when you do deep learning. You could just write it one time and then differentiate it with whatever AD system you want. And my pet project of this year is called differentiation interface.jl, and it has sort of the same idea. It talks to all of the dozen or so Julia autodiff backends, and for everyone, it reaches deep into their internals to pull out the best performance so that the users don't have to dive into the documentation of each individual package. They can just have a common syntax for all of them, the same way that Keras does it. Now, as a conclusion, it's 2024. Don't compute derivatives by hand. I am begging you. We have automatic and efficient systems to do this for you, but they come with limitations. So you need to learn to recognize and overcome them. And maybe I can, yeah, my slides have updated. So if you have a tricky 80 problem, feel free to reach out to me. My website is gdal.github.io. You can write to me by email on GitHub, on Blue Sky, because I'm no longer on Twitter. And if you have something for which you're struggling to compute derivatives and you want to talk it out, feel free to chat with me. Now, I've added a few bibliographic references, including the latest book by Mathieu Blondel and Roulet, which is really amazing in terms of the breadth of things that it covers. And I just want to highlight that we've barely touched the surface of what automatic differentiation can do, because once you know how to learn how to automatically differentiate simple functions, you can ask, okay, can I autodiff my way through a solver for differential equations, or for Monte Carlo simulations, or for convex optimizations? And the answer to all of these questions is yes, you can autodiff your way through heaven and earth if you want to, but it requires a very elegant and aesthetically pleasing blend of math and computer science. So I'll leave you to figure it out by yourselves. And I'm done here. So I guess we'll take questions. There's one by Danielle. Differentiation interface implies that users can change from a backend to another easily, or should it be done by the dev of the library that uses it? So it's a great question. And you notice that the roles of the user and the library developer are different. The role of the user is to take a library and say, okay, I want to compute gradients of some functions provided by this library. And differentiation interface is targeting these users. So to differentiate through optimization solver or differential equation solver or whatever, you can choose a variety of AD backends. Now, the job of the library writer is much harder, because the library writer needs to make sure that his or her code is compatible with a variety of AD backends, at least the most popular ones. And this is tricky because while it's rather easy to write an interface that computes gradients with all automatic differentiation systems, it is much harder to write an interface that defines these basic rules, these differentiation rules for all AD systems. So at the moment, such an interface does not exist, which means that if your code as a library developer is not natively compatible with automatic differentiation systems, you need to write what's called custom rules. And this, unfortunately, must be done backend by backend. Hopefully that answers your question.
Hey, Guillaume, we have Daniel here. Did I answer your question, Daniel, or did you have any follow-up there?
No, actually, I was just interested in about the how do you think that so many backend could be useful for the Julia community, or there is better reduce the number to concentrate more the effort?
So there are a variety of reasons why we have so many backends. Um, First reason is because they do different things. So there's two of them here: fast differentiation and symbolics. There are symbolic backends, and I told you earlier, symbolic differentiation does not scale with very big and very complicated functions. But sometimes you have very simple functions, like in differential equation solvers, and you want to find the most simplified way of expressing their derivatives. And computer algebraic systems or symbolic differentiation systems are great at that. So there's a very clear use for these types of technologies in scientific machine learning, which is a sort of different field than your standard deep learning pipelines. Other ones of these backends are forward versus reverse mode, and so we have different, implementation choices. We have Enzyme, which is based on a lower level than actual Julia code because it differentiates through LLVM code. So it's a mixture of different paradigms, different implementation techniques, historical reasons where some backends were developed by different people and learned from the mistakes of others. So some of those may be deprecated in the short to medium term because we move on to better solutions. And that's okay. And the fact that we have an interface means that we can make it easier for users to switch when there is a more efficient solution that appears. But of course, it's linked to the fact that all of these backends have very sort of low bus factors. They're developed by 1 or 2 people. And so it's rather easy to develop something that's very useful in Julia, even if you're just a single person. Whereas JAX, PyTorch, and TensorFlow are obviously much more ambitious industrial efforts. So it's not an ideal situation. I agree. We should have probably fewer options, but it's great that we can switch from one to the other rather easily because they're not coupled to a specific tensor format or to specific math operations that we need to use.
Thank you.
Yeah, Guillaume, could you discuss the differences between like the framework approach and the backend approach? It's not clear to me why we couldn't do like the framework approach in Julia.
We could definitely, and arguably maybe we should, because it would make life easier. I think part of the problem and also the beauty of these efforts is that Julia people are half ambitious, half crazy. And they set out to say, okay, we want to write the definitive automatic differentiation library that could differentiate through the whole language. But when you set an objective like that on a programming language that was not designed for automatic differentiation, then you run into all sorts of troubles. And I'm implementing a forward mode autodiff system myself these days, and I'm scratching my head as well because there's plenty of things that we need to handle that we wouldn't need to handle if the language itself was a subset that was specifically designed for autodiff, the same way that PyTorch or JAX works. So this framework approach is definitely doable in Julia. You define a new tensor type, you define new mathematical operations, and you tell the user, whatever you do not go out of this very well delimited area. You see these shadow lands out there, never go there. And that's possible, but it's also less fun. And ultimately, I think Julia developers want to do the fun and crazy and elegant and aesthetic thing. And sometimes it works out and sometimes it doesn't, but I really like it.
I see. So maybe you could carve out a sub language within Julia that's basically the main specific language. You think this would actually provide a better experience?
Or it would be a different experience. I don't know if it would be better because it would be more limiting, but it's certainly possible. And the other way around is also possible. For fun, I implemented bindings of differentiation interface.jl with JAX. So there's a very experimental package called differentiation interface JAX.jl, which calls Python from Julia to compute derivatives. And of course, it's crappy as hell and it doesn't really work well. But I like the fact that we're free to experiment this much and cross combine the different languages and frameworks.
Yeah, that's the other thing I was thinking. Is like, could we use Torch or JAX or XOA as a backend for?
Yeah, but I think the real answer is not going through Python, is going one level down to XLA directly, and that's what the project called reactant.jl is all about. It's by the same people who did Enzyme, and I think it's probably very closely linked to the future of deep learning and differentiation in Julia, is compiling this code to XLA to generate efficient functions and efficient derivatives.
Excellent. Okay, I think we're going to close here. I'll give you one last chance to advertise your YouTube channel.
Oh, yeah. I also make crazy scientific related songs, parodies of famous songs that are very cheesy. It's just me and my piano, but please don't check them out on my website. It's my greatest shame and my greatest pride.
Thank you for that. Let's thank the speaker again. I'm going to end the session a little bit early. Thanks.